All right, guys. So we are going to cover from our textbook. This corresponds with the section 3.1, like chapter 3, section 1. However, if we compare this to the AP content, that it's considered topic 2.1. So this is, we got kind of a couple different numbers going here. When we compare this to our textbook, it goes along with section 3.1. However, the title of the worksheet corresponds with AP stuff. So that's why you're seeing a different number up there. But this is all about arithmetic and geometric sequences. I preferred this to what's in the textbook, so that's why we are using this handout this time rather than the normal notes that we typically do. So, all right, let's talk about sequences. So sequences, that's what we're talking about here. A sequence, we're just going to fill in these different places. A sequence is a function that goes from whole numbers, so all of your inputs will be whole numbers, to the real numbers. So all numbers that are outputs will be real. All of the inputs will be whole. Okay, so that means that's a little bit different than your typical function, because typically we can input any real number, not just whole numbers. You can input decimals, fractions, negative numbers. It doesn't really matter. You can input anything you like to try to get an output. But when we talk about sequences, we are only plugging in whole numbers. Okay, since we aren't going to be plugging in any whole numbers, it also causes us to have graphs that are not continuous. I'm going to show you what that means in just a minute when we graph one. But essentially, what's going to happen is you can't connect the dots. And that's because you're not able to plug in fractions or decimals. So none of your x's will be fractions or decimals, none of the inputs. So it can't connect. But you'll see that in a minute when we graph one. We're going to start off here with example 1. It says we're going to consider the sequence defined, and we're just going to practice how do you read these sequences, how do you treat them like functions, and it really is a function. It's just a slightly different notation. So if we have this function a sub n, that's a little subscript, a sub n equals 4n minus 3, this is like a little linear equation, and it works the same way when we want to try to figure out inputs and outputs. They're asking us to find a sub 1. It's basically the same thing as if I had a function a of n. This is a of 1. You're going to plug in that 1 everywhere we see an n. So we're going to start off with that. A sub 1 is going to be 4 times the n value, which is 1, minus 3. 4 times 1 is 4, minus 3 is 1, and there's your answer. If instead we had our input as 7, our output would be 4. Oh, that's not a 4. Whew. Hold on. Let me get my whiteout handy. Okay. So if I have a situation like that, let me try that again. We have 4 times my input, which was 7, minus 3. 4 times 7 is 28, minus 3, 25. Okay. So yeah, that's how you deal with sequences when they're written in a function form. And you can just find any value in the sequence that you need. All right. Now, some important information about a specific type of sequence. We're going to study 2 different types of sequences, arithmetic and geometric. So arithmetic is what we are starting with here in this video. This video is going to be all about arithmetic. And then the next one, we're going to talk about geometric. So definitely make sure that you view both. But this one here, arithmetic sequences are like linear functions. Okay, so that's number 1. It's like linear. You're going to see that there is a constant rate of change, a common difference between each of the values in the sequence. So you're going to see that constant rate of change, which we usually think of as slope. Arithmetic sequences, they behave like linear functions, except big idea, they are not continuous. They're not going to connect. And again, you'll see how that works in a few moments. Now, there's a few things here. We've got some equations that we can use. And honestly, y'all, you can use different equations. However, you can technically use either one of these for pretty much any of the problems. You can, whenever you happen to write an equation, if they want the most simple one would be using this first one. Let's talk about what some of these components are. This a sub 0 is considered the initial value. Okay, so that's like your starting place. Your initial value is your starting value. D in this situation is going to be considered your common difference. Okay, and then this a sub k is actually, it's kind of crazy, but it's the kth term in your sequence. Okay, which I know sounds a little bit wild, but if they give you a term in the sequence, you can represent it as like a generic term. Okay, and we'll discuss that when you see it in a few minutes. But you've got two different equations, and whatever you're given to use, it may be easier to use one formula or the other. You can kind of get away with using either one of them if you know what you're doing. So it's not just a one way or the highway type of scenario. A lot of these things you can find multiple different ways to represent values and get the answers. Okay, we're going to work one here where we graph it. I told you we would. We need to make sure that we understand how all of that graphing actually works. So look here at this first example, okay? They've given us, this is an arithmetic sequence. I can tell that because the equation is linear. You can also tell that because, let's see, if we make a table of values, look at this. If I plug in, now remember how we said all of your inputs have to be whole numbers. So I can't plug in any negatives. I can't plug in any fractions or decimals. So just keep that in mind. The smallest whole number is 0, and then they go up from there. 0, 1, 2, 3. And I could keep going, but we're going to just do that many. Well, if we plug in a 0, 3 times 0 is 0, plus 1 is 1. If I plugged in a 1, 3 times 1 is 3, plus 1 is 4. If I plug in a 2, 3 times 2 is 6, plus 1 is 7. And if I plug in a 3, 3 times 3 is 9, plus 1 is 10. And again, we could plug in values all day long if we really wanted to, but this is perfectly fine. I'm not even going to be able to fit all of these on the graph. So we're plotting these exactly the same way you plot normal points. 0, 1, you're going to go 0 on the horizontal up to 1 on the vertical, and there's a point. 1, 4, I'm going to go 1 up to 4, plot a point. All right, 2, 7, 2 all the way up here to 7. Now 3, 10 doesn't even fit on the graph, but I want you to see this is linear, right? I just can't connect them because it's not continuous. Here's what I'm saying. All of my inputs had to be whole numbers. I'm not even allowed to try to plug in a 1.5 or a 0.25, right? I'm not even allowed to plug those in because of the definition of a sequence. So because I can't even plug in values between like 0 and 1, there's no way for me to plot or connect these because I can't have anything between those two graphed, okay? Because I'm not using any fractions or decimals as my inputs. So I can't connect them. They are not continuous. I'm going to say it over and over every time we have a graphing scenario. All right. Going down here to example 2. They're asking us on this. Let's zoom out a little bit so maybe we can read the whole thing and then I'll zoom back in. So example 2, they said for each of the following, determine if the sequence could be arithmetic. If yes, identify the common difference. So let's zoom myself back in. Here for part A, they've given me a sequence. They said S sub n equals n squared minus 3. Now, some of you guys may be able to look at this and say, well, that's not linear, so it can't be arithmetic. And you would be right. However, we want to make sure that we have the correct argument for, and make sure that we're using the mathy terms for this. So I'm going to say, let's do the same kind of thing we did in the last problem. It also helps if we stay consistent, right? So if we make ourselves a little table of values and we plug in 0, 1, 2, 3. Again, I could keep going, but I'm just going to do that many. If I plugged in a 0, 0 squared is 0, minus 3 is negative 3. If I plug in a 1, 1 squared is 1, minus 3 is negative 2. If I plug in a 2, 2 squared is 4 minus 3 is 1. And plug in a 3, 3 squared is 9 minus 3 is 6. So here's what I want you to see, all right? If we go from one term to the next, from negative 3 to a negative 2, that value went up 1. If I go from a negative 2 to a positive 1, that went up 3. And from a positive 1 to a positive 6, this went up 5. We do not add the same number every single time. We added 1, add 3, add 5. That is not a common difference. So we're going to say this is not arithmetic. So no, there's no common difference. Okay? Not arithmetic. All right, let's look at the next one. Now, some of y'all may be looking at this and say, yes, it's linear, therefore it's arithmetic. However, let's make sure that we have another good way to show it. N and A sub n. 0, 1, 2, 3. Plug in each one of these. It's maybe a little bit tougher to do in your head, but you can totally do it. If I plugged in a 0, 2 times 0 is 0. 6 minus 0 is 6. If you plug in a 1, 2 times 1 is 2, right? 6 minus 2 is 4. If you plug in a 2, 2 times 2 is 4. 6 minus 4 is 2. Plug in a 3. 2 times 3 is 6. 6 minus 6 is 0. And then it keeps going. So here's what I want you to look at, okay? From one value to the next, from 6 to 4, that went down 2. From 4 to 2, it went down 2. From 2 to 0, it went down 2. Do you see how there's a common difference? It changed the same amount each time. And so we can say, yes, this is arithmetic, and our common difference is a negative 2. Okay? What if they give us the sequence in a little bit of a different way? Okay? What if we have, instead of a table or even instead of a formula, they just give us the sequence? This is the exact same thing, guys, as our list from our A sub n part. So honestly, these are a little bit less work if we work it in that same way, or if we justify it that same way. These are a little bit less work because it's like that part's already been solved for you and it has the whole sequence there. So I want us to look at the differences here. We're going to do the same thing we did before. From negative 7 to a negative 2, this went up 5. From 2 to 3, this went up 5. From 3 to 8, it went up 5. 8 to 13, up 5. We have the same change each time. That means, yes, it is arithmetic. That common difference was a positive 5, so 5. Look at part D. From 1 to negative 2, this went down 3. Negative 2 to a positive 3, this went up 5. Positive 3 to a negative 4, down 7. And then negative 4 to 5 is up 9. So there's definitely some kind of like pattern here using odd numbers, and you subtract it and then you add the next one. But it's not arithmetic because it's not the same thing every single time. So because we're not adding the same thing every time, no, this is not arithmetic. There was no common difference. Okay? So far, that's just us kind of introducing the idea of sequences and arithmetic sequences. But let's see, what if they want us to actually come up with an equation for some of these? So I'm going to write on here, well, okay, you can write it on the paper if you want to. On our last page, I want you to just keep this middle box handy and be able to flip back to it if you need to. I'm going to be pulling from these two equations. Okay, they're both really, really handy equations. And for us to decide which one we want, you're going to kind of need to keep them handy, okay? So if possible, I would like to try to use that first one, but it's not always a thing. So it just kind of depends. You can use both, either one, really, but sometimes it's easier for one than another. So The first equation is the most simple one. It is, well, bring that back over here real quick. I know this is a different color, but the first equation really is more simple than the second. It's using the initial value rather than these k's and the n's. So if possible, that first one would be really nice, but it's not always super handy. So it just kind of depends on the problem as to which one might be a little easier. This question, for example 3, it says, let our sequence be an arithmetic sequence. So it'll have one of those patterns where we have a sub 3 is 8. The common difference is -3. They said find an expression for a sub n. Use the expression to find a sub 12. So really important to note, guys. We got our common difference right here. But what on earth is going on with this term right here? They're telling me that the third term in the sequence is 8. Okay, so what we should really be looking at is how can we represent this? Well, I'm going to choose that first formula for a moment, and I want to show you what we're going to do with it. This is not the first term. Okay, plus d times n. So this is definitely not the first term in the sequence. You see, this is a sub 3, not a sub 0. Right? So it is definitely not the first term in the sequence. This is, it's not the initial value. This is further along the sequence. But one thing that we can do is, you see how we talk about this a sub n? I could let's just say that n was 3 for a moment. Let's just make that argument. If n was 3, then this term would be a sub n, if n was 3. And that would mean that a sub n was actually 8. So the purpose of this argument, we can talk about having an nth term, okay? Just like the previous page, we talked about like a kth term. An nth term, this is just talking about some random term in the sequence. The third term, well, that would be if n was 3. A sub n, a sub 3 would be 8. And then what we can do with that is we can actually plug those values into the function. A sub n, if we just replace that with an 8, we don't know the initial value, but we're going to be able to solve for it. We do know that your common difference is a -3, and we said, what if n was 3? Right? If I just plug these values in where they fit on that equation, we're going to be able to solve for the initial value. So look here. This would be a sub 0. -3 times 3 is a -9. Add 9 on both sides, and my initial value is actually 17. So what I can do is actually write an equation using that. We can go back to that initial equation that I was working with and just replace the n's back. They want an expression for n. So put the n's back. But instead of putting the a0, we're going to put the 17 that we know it is. Plus, we know, pause. Since my common difference is a -3, it's actually a little bit cleaner just to say -3. You could say plus a negative, but it's cleaner to say minus. And then we're going to say that we're going to put the n's back, right? So that we can have an expression for n. That would be a really nice equation to be able to solve for any term in the sequence. And they specifically, on this problem, ask us to find a sub 12. So we're going to plug in a 12. This would be 17 minus 36, and that would give us -19. You might be saying, I thought we can't have negative numbers. For your input, n can't be negative, but the output can be negative. That's okay. All right, let's look at example 4. All right, a slightly different scenario here, y'all. Instead of a term and the common difference, this time we've been given 2 different terms. They said find an expression for a sub n and use the expression to find a sub 24. So here's what I'm going to do here. I could try to force using either one of them. I could figure out what the common difference was, and then I could do the exact same thing as I did before. You might be saying, how would I find the common difference? Keep in mind that arithmetic sequences are linear. This is like an x and a y, an x and a y. If you found the slope, that's the same thing as a common difference. So you could totally go about it that way. However, I'm going to try to show it the way that they want us to properly do it, okay? but that is a way you could go about it and relate it to things that you know. Okay, the other way is to choose one of these to be like k's and the other to be n's, and talk about having a kth term and an nth term. Okay, so if I did this, I would say this guy would be my k and this be my a sub k. You might be saying, how do you know that that's k and not n? It doesn't matter. On the arithmetic sequences, the order of those really doesn't matter. As long as a subscript is k or n, and then that whole number or that output there would be the a sub k or the a sub n. So if I choose this one to be k, the other one would be n. And this guy would be a sub n. And then what I can do is use that slightly more complex equation, but we can plug in the values that we know. So I'm going to rewrite that generic form. It says a sub n equals a sub k plus d times n minus k. Well, if I said that a sub n is going to be 9 for this purpose, a sub k was 7, plus we don't know the common difference, but n was 6 and k was 2, then what we're able to do here is solve for that common difference. Subtract 7 on both sides, and you end up with a 2 equals d times 6 minus 2, 4. If you divide both sides by 4, 2 divided by 4 is 1/2. That's our common difference. So that would give me a way to write my equation. Now, I know the equation's a little bit weird. If you really wanted to, you could then use this common difference and one of those terms to figure out the initial value and write that. But it didn't say I had to use that format. It just says in the problem to find an expression for a sub n, and they didn't really get any more specific than that. So one thing I could do is just take this equation that I have here in blue, and I can rewrite it with the n's back in place, but replace all the other things with the numbers that we know they are. So I could write it in terms of n, a sub n equals, but we let k be 7. We know our common difference is 1/2. Put the n back in, but the k we had chosen earlier was a -2. That is an equation that we can use. It's not the only one, but it's one of them. And what I can do with that is then find what they want. And on this problem, they had said find a sub 24. So that's what we're going to do. 7 plus 1/2 times 24 minus 2. And from there, it's just solving. 1/2 of 22, 7 plus 11, 18. There's our answer. Okay, one more example for this video, and then we are going to call it quits for arithmetic sequences, okay? So this one's got a graph to go along with it. It says several terms of the arithmetic sequence are shown below. Find an expression for a sub n and use the expression to find a sub 17. So on this one, there is a little bit of a trick I would encourage you guys to do, which is to look at your graph and use that to find what your different terms in the sequence are. If your n's, which you'll see here, this is my axis for my n's, the input, if my n was 0, A. Am I doing putting G's on here? Should be A. Okay. If my A sub 0 is 8, you see that point there? That output was an 8. Then this one was A sub 1, right? If my input is a 1, my output is 6. I'll keep writing weird symbols. Here we have A of 2, which is going to be 4. Why am I putting parentheses, y'all? It is the end of a very long day. Okay, over here we have A of 3. Let's see if I can write the right symbols. 3 was 2. And then down here we have one more. A of 4. Output is 0. Okay, so we got a lot of things here. Here's our sequence. It went from 8 to 6 to 4 to 2 to 0. You may be able to tell the common difference here. If you can't, you need to do some subtraction. Okay, it is going from 8 to 6. This went down 2, down 2, down 2, right? So my common difference here is a -2. For the problem, it says several terms of the arithmetic sequence are shown. Find an expression for a sub 0 and use the expression to find, a sub n, and use the expression to find a sub 17. So a nice feature here is the fact that my a sub 0 is 8. They've given me that initial term, so I'm going to make note of that. This was the initial value, and we know that our d term was a -2. And if you know those values, guys, we have that expression for a sub n that uses the initial as well as your common difference. And we just plug the numbers in, right? A sub n equals my initial value. Now my d is negative, so I'm going to say -2n, and there's a nice little equation. If we use that to find our a sub 17, y'all, that should just be a sub 17 equals 8 minus 2 times 17. That's 8 minus 34, which is a -26. Okay? So that is arithmetic sequences. And y'all, definitely stay tuned for the next video where we discuss geometric sequences. They are a little bit different, but it's a lot similar. So there's a lot of similar techniques that go into play with it, just slightly different patterns. That's all. All right, guys. Look forward to seeing you in the next video. Bye.